Hello everyone, welcome to GATE Academy Global. Today we will be discussing about the Fermi level numericals, as we have seen in my thumbnail also it is given. So yesterday we have discussed so many important points and formulas about the Fermi level. I think those who are attending the classes right now, they have attended those classes also, because without having the formula knowledge, or we can say the concept behind the Fermi energy level, it will be very tougher to discuss about the questions. So those who has attended and those who knows the formulas and the concepts of Fermi level, they can attend the classes, they will understand. And those who are attending this one for first time, they can also attend, because I am going to discuss about each and every points of the Fermi level questions. And we are getting so many questions in a GATE examination also, that depends upon the location of Fermi level in a device, or location of Fermi level in a semiconductor. So right now I can see Sridevi, Sarika, Narendra Reddy, Makwana, Neil and Lakshmi is attending, and Virat Bhatia. Best PD course, EDC is best most conceptual. Yes, thank Virat Bhatia for your appreciation. And I think those who are from electronics branch basically, and they have to know the basic concept behind EDC in more deep way, because without understanding the basic concept of EDC, you are unable to fight the interviews or the conceptual questions of GATE examination or any other competitive examination, of course. And if you are trying to have a good job, okay, in VLSI companies or microelectronics companies, then you must have to know everything about the Fermi level, location of electrons and position of electrons and the energy of the electrons, and how to describe the basic device structure, and how to design the structures. Everything you have to know, and the following ideas will be given by the subject EDC. So you have a sound knowledge of EDC if you want to progress in your own field like electronics. And of course many electrical students, they must choose this particular microelectronics subject in as a specialization branch in their MTech. So they has to know these following concepts that I am going to deal in this particular subject. Okay, so shall we start the session? In today's session we are going to take some questions, and before taking some questions, we are going to have the revision of the formulas that we have already seen. Sir, all the concepts will be covered in crash course. Great effort by GATE Academy. Yes, we are going to cover all the concepts. Okay, so yes, we are going to start the session, and in this session we are going to use the formulas, and I am writing those formulas first of all. And in the previous session we have seen that we are having some of the conceptual points about the intrinsic and extrinsic semiconductors, and of course we have seen some of the formulas also. So just I am revising those formulas. So first one, we are talking about intrinsic semiconductor. Very fastly we are going to revise the formulas, because this is the crash course. We must need to understand the concept behind the formulas. If you want to do a good deal of the questions that is coming in the GATE examination, then many of the students has some doubt. What is the doubt? The doubt is that if we are not having the concepts behind the derivation part, then can we deal the question of GATE examination? Of course you cannot. So we must have some steps how. Of course not every step, but you must have the steps how a particular formula going to be derived by using which particular steps. So if you know that one, then only you can get a good deal of the questions that is coming in your upcoming examination. So it is not only that you should know the final formula, it is also mandatory that you should know the steps how to find those formulas. Okay, that is also mandatory to know. Without this one we cannot deal questions of GATE examination, because in GATE examination they will be giving the questions that is based on not only the formulas but the concept behind those formulas. Okay, so I must tell everyone who want to attain a good score, okay, those who don't want to attain a good score, they want to only qualify or crack the GATE examination. So if they knows the formula, that is okay, but if they want a good score, then definitely you must have to know each and every formulas in addition to how to deal or how to derive those formulas. Okay. So derivation part we have already discussed in our full course, and we are going to take the crash course in this. Somewhat we are going to see the steps, but not all the steps we have seen or we are going to see. Okay, but we are going to deal with the formulas very frequently in each and every questions. Okay. So if you are taking the intrinsic semiconductor, then we know the what is the location of intrinsic semiconductor, the location of Fermi level. Okay. So if you know the location of Fermi level, then we should have the good concept, that is EFI. It is the location of Fermi level in intrinsic semiconductor, I representing the intrinsic. So we must write here, this is EC plus EV divided by 2 minus, we should write this is KT divided by 2 and ln NC divided by NV. So here this NC and NV are nothing but the, okay, this will be of course the midpoint of what? Midpoint of energy gap. Okay. So whenever we are having the intrinsic semiconductor, of course it is located at the midpoint of the energy gap. But so if you say like this, then this is the center. Okay, we have a questions based on this particular formula in our previous examination. I think that is in 2019 we have a questions that is based on this particular formula. And this is nothing but the center of forbidden gap. You must write here, this is nothing but the center of forbidden gap. Center of forbidden energy gap, this much point. Okay, because EC is the lowest location of the energy level or energy states in the conduction band, and EV is the highest position of energy states in the valence band. So if you take that is divided by 2, then this must be the center. Then we are having some extra part here. Okay, we must have to know this part also. We are having an extra part in addition to center. This is an extra part. How to deal with this extra part? We can deal with this extra part by knowing the formula for NC and NV. What is NC and NV? We already know that NC is the effective mass of NC is the effective energy states at the edge of the conduction band. NV is the effective energy states at the edge of the valence band. So we are having the formula, that is NC is equal to 2 into, this is 2 pi mn into kT divided by h square, and of course we are having this is raised to 3 by 2. So this is one formula that we should know properly. Without knowing this one, we cannot deal with this one, this particular formula. So this is one of the formula which is representing the effective states present at the edge of the conduction band, and this concept is from density of states. So from this particular formula, which consists of, this is 2, that is a numeral value which is having no any variables, that means this is a constant. This is 2 pi, again it is constant, and we are having Mn. Mn is nothing but the effective mass of electrons. So always we have already discussed in our previous lecture that effective mass always consists of or we can always use this effective mass whenever the electrons are present inside a solid. So whenever the electrons are present inside a solid, not present within a vacuum where we are having isolated electrons, these electrons will get affected by the presence of different atoms in the neighbor of this electron, because of it this electron is experiencing a force, and whenever the electrons is experiencing a force, then definitely we are having effective mass. I think those who are from electronics branch, they have listened this word effective mass, and always this effective mass are compared with the normal mass of electrons or the original mass of electron, that is 9.1 into 10 to the power minus 31 kg. So whenever we are comparing this one, we are going to normalize this one or take the ratio of this particular mass with effective mass, and then we are going to find out what will be the ratio. Okay. So here, so if you are won't understanding this particular point, then definitely we are going to deal some numerical problem based on this particular formula or effective mass, then you are going to know about this particular effective mass, how to write the effective mass value and how to deal with this formula. Okay. Now, right now I can see that we can since it is having many terms which is constant, that is H is Planck's constant, K is Boltzmann constant, T is temperature at temperature in Kelvin. We must write at different temperature we are having different effective density of states at the edge of the conduction band. So, based on the temperature we can say that the value of this temperature will vary the density of states. Okay. So, I just want to write after dealing everything, this is Nc is equal to 4.82 into 10 to the power of 15. Then we can write this is Mn into this is T divided by this is original mass raised to 3 by 2. So, this is the another way of writing this particular formula. So, we have taken the constant together and we get multiplied and division whatever is present there. Then we are writing the similar particular formula in this way also, 4.82 into 10 to the power 15 Mn into T raised to 3 by 2 divided by M, where Mn is the effective mass, and just now I said that this effective mass is always written with the ratio of original mass. So, here M is the original mass and Mn is the effective mass. So, these two things will be taken together for understanding the concept behind this extra value. Okay. Then we are similar way, we can write the similar thing, that is what is that, sir, we can write the value of NV also. So, how to write NV? So, most of the students know this particular factor, that is again we can 2 pi. So, instead of Mn we are writing Mp here. Okay, take care. And here we are having Kt divided by h square raised to 3 by 2. Okay, we are writing in this way. So, the unit is per centimeter cube. Yes, this is the density of states and the unit is here. This is per centimeter cube is the unit. Here also we are having per centimeter cube is the unit, and here also we are having per centimeter cube is the unit. I am just talking about the formula. You have take care this of the units also, because this is density of states. So, after understanding this concept, we can write this NV can also be written as NV is equal to, this is 4.82 into 10 to the power of 15, and we are writing this is MP into T divided by M raised to 3 by 2. This will be the formula, and the unit again is per centimeter cube. So, what is this M? Already we know this is the original mass, and original mass never change because this is the mass of electron in vacuum, and Mp and Mn is the effective mass. So, if I ask one thing that what is the difference between these two formulas? The difference between these two formulas is nothing but the effective mass of electrons and effective mass of holes. So, if I take the cases, I just want to ask the similar thing, the quiz questions, so that you will have some interesting facts about this. So, if I write that if the effective mass of electron is equal to the effective mass of hole, then I just write this one, then the location of Fermi level in an intrinsic semiconductor. So, the options are center of forbidden gap, above the center of forbidden gap, below the center of forbidden gap, coincide with edge of conduction band EC. So, I can see Prithvi Srinivas has answered this question and everyone is thinking. So, I just ask that if the effective mass of electron is equal to the effective mass of hole. So, we can change this question in a similar way and we just made another quiz. This is quiz number 1 and this is quiz number 2. How we can make then another quiz? If Mn is greater than Mp, then, so we just write, then the position of Fermi level in an intrinsic semiconductor. Okay, so I just changed the question. The effective mass of electron is greater than the effective mass of hole. Then we are having this is at the center of forbidden gap. What is the reason? Because if the effective mass of electron is equal to the effective mass of hole, then what will be the equation? Then NC will become NV, because the only difference that we have seen between the NC and NV formulas is nothing but the effective mass of electron and effective mass of hole. So, if you wrote this formula for getting the answer of question number or quiz number 1, then we are having NC by NV that will be equal to 1 and ln of 1 that will be equal to 0. Then we just have this is EC plus EV divided by 2 only, and that means it is exactly located at the center of forbidden gap. Okay. So, I just write this particular formula for getting the answer of this question, and I think many of the students has done well because they have answered very fastly, and those who are answering very fastly, they will have the good concept over this one. So, we have to find out the Fermi energy level in an intrinsic semiconductor, and this is EC plus EV divided by 2 minus of KT divided by 2 ln NC divided by NV. Okay. So, I just write here, if we have Mn is equal to Mp, then this implies NC is equal to NV, and in that condition EFI should be equal to EC plus EV divided by 2. This will be the formula. And if you want to know about the location or the position of Fermi energy level, okay, for question number 2 below the center of forbidden energy gap, because this negative one which is present in this formula is very important for answering quiz number 2. So, if I answer this quiz number 2, then we must have the following concepts over this one. What is the concept, sir? Again we have to write the formula, the location of Fermi energy level in an intrinsic semiconductor. This is become EC plus EV divided by 2, and we are having minus of KT divided by 2 ln, and NC, if the effective mass of electron is greater than the effective mass of hole, then this NC will be greater than NV. If NC will be greater than NV, then definitely this particular whole thing that is present inside this bracket, okay, will become positive, and it will be, if it will become positive, then definitely EC plus EV divided by 2 minus that particular magnitude which we are getting from this particular equation. So, I am not talking about temperature, because temperature will be of course greater than 0, okay, not absolute 0. Then we are having the location of Fermi energy level, that is EFI. EFI is the intrinsic Fermi energy level. It locates above the center, okay, not above, it is of course below. Let me clear this one, because this negative sign, okay, because of this negative sign, I just write here by highlighting this word, this is below the center of forbidden gap, okay, center of forbidden gap. So, we are having EC plus EV divided by 2, that is nothing but the center, and we just write the equation in this way, that is EC plus EV divided by 2. This must be the center minus of EFI. E is having some positive value. This is KT divided by 2 and ln NC divided by NV. So, if it is having some particular magnitude which is a positive value, then definitely the location of Fermi energy level is below the center of forbidden gap. Where is the center locates? This must be the center. Okay, this must be the center minus this is the location of Fermi energy level in intrinsic semiconductor for this particular condition, and this is having some positive value. If it is having some positive value, then definitely the location of Fermi energy level must be below the center of forbidden gap. So, we just draw this one. So, we have two lines which is representing the energy, this must be representing energy. So, energy in which? Sir, energy in electron volt, and this is representing the distance in centimeter. Okay. And if this is representing the energy, then it also representing the location of Fermi energy level. So, I must draw two lines to represent the position of what? Sir, the position of EC and EV, and we just take a location which is locating exactly at the center of this forbidden energy gap. So, I must write here that this must be the position which is known as EC plus EV divided by 2, which is nothing but the center, and the Fermi energy level which is known as EFI will be located somewhere here. So, I just draw a line somewhere here, and I must say this is the location of Fermi energy level EFI. So, the difference between these two will become positive, that is EC plus EV divided by 2 minus EFI will become a positive value. So, which represent that this is located at the below the center. Okay, this must be the center, and this must be located below the center of forbidden gap. So, this particular distance can also be written as this is KT divided by 2 and ln NC divided by NV. Okay. So, we must know this one. If I change this quiz question, and if I write here, that is if MP is greater than Mn, then the position of Fermi level in an intrinsic semiconductor, it must be above the center of forbidden energy gap. So, we must have to know for all these things in a proper way. So, this is the following points, and we can find out the energy gap, the distance between the two positions of EC and EV. So, for finding that one we can write here. Okay. So, finding that one, the distance between the forbidden energy gap can also be found, and now we are taking the next one, that is second one. Okay. So, what is the second one? I am talking about an extrinsic semiconductor, and this extrinsic semiconductor must be an N-type semiconductor. In an N-type semiconductor, we know what will be the location of Fermi energy level, because this concept is based on Fermi energy level. So, we must find the location of Fermi energy level in an N-type semiconductor. Of course, this is EC minus. Okay, this is EC minus, and that is nothing but KT ln, and we must write this is NC divided by ND. And we know there is two dependency of this position of Fermi energy level. What are the two dependency? One is the position of Fermi energy level, position of Fermi level. Okay, you just revise these things properly. Depends on, we just write here, this is depends on two things. What are the two things? Of course, it is depending on the first one, that is temperature, and second one, that is the dopant atoms. And what are those dopant atoms? Sir, Nd is the dopant atoms. Yes. And second one is If I take the second, this is third one, and third one extrinsic semiconductor, and we must write here this is suppose a p-type semiconductor. We know that where this Fermi energy level goes when we increase the temperature. So, write the answer in your comment box where the Fermi energy level goes if you increase the temperature, and where the Fermi energy level goes if you increase the donor atoms or dopant atoms concentration. So, till then I will write the position of Fermi energy level in a p-type semiconductor. This is EFP, okay, you just answer in your comment box. This is EV plus KT ln, and this is NV divided by NA, okay, this is the another formula. Toward the center of forbidden gap, yes, you have answered correctly. So, I just ask these two questions. What are the questions? I have one question, okay, I have one question. That question is based on that if temperature increases in an extrinsic semiconductor, I just write here, in an extrinsic semiconductor, N-type and P-type, then I just ask where the Fermi level goes. So, if you increase the temperature, the Fermi level moves down. If you are writing Sridevi like this, then this is about only for N-type semiconductor. It will move down or move up. So, you just not answer in this way, move down, move up. You just answer that the position of Fermi level, if you increase ND, the Fermi level moves upwards. Okay. So, I just write here, if you are talking about this temperature and what will be the answer of this particular question. So, I just write here the Fermi level moves closer and closer to the center of forbidden energy gap. Because at some temperature it will move to the center, not exactly it will move to the center, okay. It will be moving closer and closer as we are increasing the temperature. Suddenly it will not going to the center of the energy gap, okay. You just not answer in this way. It will be present at the center. It will move, it is moving closer and closer to the center of forbidden energy gap, and at some particular temperature it will be located at the exactly at the center of forbidden energy gap, and at that particular position when it or temperature when it is located at the center of forbidden energy gap, then the semiconductor will become an intrinsic semiconductor. So, if you are writing in this way that it is locating at the center, then you must saying that the semiconductor will become an intrinsic semiconductor. This is not the correct way of writing the answer. So, you must write that the Fermi level moves closer and closer to the center of forbidden energy gap, and if it is moving towards the closer and closer to the center of forbidden energy gap, then at some particular temperature when the extrinsic semiconductor will become an intrinsic semiconductor, at that particular temperature the semiconductor Fermi energy level will located exactly at the center of forbidden energy gap. So, we just have to do some practice or practical, so that we can able to find out when the extrinsic semiconductor will become an intrinsic semiconductor. Then only we can say that it is located, the Fermi energy level is located at exactly at the center of forbidden energy gap. So, in this way we have to answer. So based on the dopant atoms also we can write the answer. So as we increase the dopant atom in case of n-type semiconductor, that is donor atoms, the Fermi energy level will moving towards the inside or towards or inside the conduction band, or as we are increasing the acceptor atoms in case of p-type semiconductor, the Fermi energy level is maybe or going inside the valence band. Okay. So it depends upon how much dopings we have done. So if I write in this answer, okay, so if I ask you another question, what is that question? The question is like this: if I write that if we say if we write that is NC is equal to ND. So if we write in this way, then what will be the location? Then what? Location of EFN in N-type semiconductor. Just answer this question. देखना comment देख. Okay, so if NC is equal to ND, then what will be the location? Then what will be the location of EFN in the N-type semiconductor? So is there any answer? EC at EC. Okay, I will have the answer, and the answer is, it is EFN coincide with the edge of the lowermost energy state of conduction band EC. Okay, many of the students are saying that nobody is answering their question if they have purchased GD. So who is not answering, I don't know, but if you ask some questions to me, then I will definitely answer your question, and this is the way by which I am providing you the answer of the each and every diodes that we have in your GD course or PD course, whatever will be there. So always blaming someone is not going to upgrade you. Okay. So if you have anything with you and you are not able to answer the problems that we have, and you are blaming somebody else for problems that we have, then you will not going to upgrade yourself anytime. Okay. So take this particular line in your mind so that you can cope up with this world. Otherwise, every time you have the blames that for your failure, and you are always doing committed mistakes and you are blaming somebody, then you will not going to grow. Okay. So this is my words, and you just make these words. So Utkarsh, Vaibhav, if you are watching these lectures, then you just take care of yourself. Okay. And I have these particular points. Okay. Then we are going to solve some numerical problems based on this one. So this is one numerical problems. A germanium sample is doped with phosphorus to an extent of 1 in 10 to the power 8. Assuming effective mass of electron is equal to half of its corresponding true value, given germanium concentration is equal to 4.41 into 10 to the power 22 per centimeter cube, the location of Fermi level is. So how many of you did this question? Okay, tell me. This is the first one, a germanium sample. So always we are having the sample either made up of germanium or silicon. So here right now we are having germanium sample, and the density of atoms which is present inside the germanium is given already. So Lakshmi, which question you have answered right now? Located at center. I think this is the question that I have been asked. If Nc is equal to Nb, then what will be the location of EFN in n-type semiconductor? EFN coincide with the edge of the lowermost energy states of conduction band. This is the right answer, Lakshmi. You just take this particular concept in your account. Okay, just like Hemant has answered correctly, and Sridevi has answered correctly, coincides, and Prithvi Srinivas is also answered correctly. Okay, so in this way we just make questions. Wherever we are having confusion, we can make questions, and based on that questions we just can answer the question properly. So we have a question right now here, that is numerical problem, and based on this numerical problem we are going to see what is the given data. So first of all, we just have seen that a germanium sample is doped with phosphorus. So suppose I have a germanium sample. Okay, I just take a germanium sample like a box. So this is a three-dimensional view of germanium sample, suppose, and this is doped with what? Sir, this is doped with what? This is doped with phosphorus. When we are talking about phosphorus, so we have adding some phosphorus atoms. Okay, so when we are adding some phosphorus atoms to this particular semiconductor, okay, so when we are adding some phosphorus atom, this phosphorus atom act as a donor atoms, and if it is acting as a donor atom, then definitely the semiconductor will become an n-type semiconductor. So whenever we are having n-type semiconductor, we have to think like an n-type semiconductor in this particular question. Assuming effective mass of electron is equal to half of its corresponding true value, that means again one given data is present here, and that is nothing but the effective mass of electron is equal to half of its corresponding true value, or we can write in this way, that is effective mass of electron divided by m is equal to 0.5. So nobody in this world is going to give you the factor how to find out this effective mass, then always they are providing you the effective mass, because this effective mass is measured in different condition wherever the electron is present inside a solid. Okay, this is the practically found value. Given germanium concentration, okay, germanium concentration means what? Sir, means that if you make a small volume inside this semiconductor, whatever will be the dimension, and if this small volume is having a dimension of 1 centimeter, 1 centimeter and 1 centimeter within a large dimension or the bar that we have for your practical, then within this we are having small atoms which is present like this. So we must need to know what is the concentration of these atoms, and in my previous lecture I have given you the formula how to determine the concentration of atoms within a large volume of the semiconductor bar. Then we are having this particular concentration is given here, and that is nothing but 4.41 into 10 to the power 22. So this is the following things that is given in the question, and based on this question we have to find out the location of Fermi energy level. So if you want to find out the location of Fermi energy level, then definitely we should know the formula. What will be the formula? Sir, formula means for an n-type semiconductor, yes. So we are going to solve this particular question for an n-type semiconductor. If you are having an n-type semiconductor, always we have to think about the location of Fermi energy level in an n-type semiconductor. This is nothing but EC minus this is KT ln, and this is NC divided by ND. So what are the things that we have in this question? We have to think about that one, and by that particular thing we have to find out the location of Fermi energy level. So whenever we have the question like this, we can find out the relative position of Fermi energy level. So what is the relative position? We can find out what will be the relative position with respect to the lowest energy level of the conduction band. So whenever we are finding the relative position, then we must write the equation properly in this way. This is known as the relative position of Fermi energy level with respect to the lowest energy level of the conduction band. And by using the formula, that is KT ln and Nc divided by Nd. So whenever temperature is not given, so we know what is kT. kT is nothing but the energy, because this is nothing but Vt and kT is equal to Vt is nothing but the energy. So if T is not given, I just write here, if temperature is not given in any question that we have in your exam, then always assume the temperature is equal to 300 Kelvin, which is nothing but the room temperature. And at T is equal to 300 Kelvin, we know the value of kT. Okay, what will be the value of kT? This is 0.026 electron volt. This will be the value at room temperature. Already we have discussed this one. And now this is the first thing, and now we just want to find out what will be the value of Nc. So Nc is equal to, sir, you just said that 4.82 into 10 to the power of 15, and we are having this is Mn into T divided by M raised to 3 by 2. This is the formula, and we have Mn divided by M also in our given data. So we just write here, this is 10 to the power of 15 and this is 0.5 and temperature is equal to 300 Kelvin. Okay, raised to 3 by 2. So this is the formula by which we can find out the value of Nc. So those who are using the calculator, they can tell me the value of Nc here, and the value of Nc by using this particular formula is 8.85 into 10 to the power 18 per centimeter cube, I think. So here we are having this particular value, this is 8.85 into 10 to the power of 18 per centimeter cube. This is very large value. That means this is nothing but the density of states, 8.85 into 10 to the power 18 per centimeter cube. And next, we don't know the value of Nd here. Do you know? Yes, sir, we don't know. But we know the value of, or we can have, what is Nd here? Sir, Nd is nothing but the density of Nd is density of donor atoms. And we know one thing from this question. What is that thing? Sir, a germanium sample is doped with phosphorus to an extent of 1 in 10 to the power 8. From this given data, we can find out. So, what is the ratio? 1 in 10 to the power 8. What is the meaning of this one? Most of the students don't know the meaning of this one. Now they are going to know. 1 in 10 to the power 8 means, it means 10 to the power 8 atoms of germanium consist is, or we can say is doped with one atom of phosphorus. 1 atom of phosphorus. 10 to the power 8 atoms of germanium is doped with 1 atom of phosphorus. Okay. In that condition, we just write that since we know the density of germanium atoms, what is the density of germanium atom? It is given in the question, 4.41 into 10 to the power 22. So 4.41 into 10 to the power 22 atoms of germanium will have how many atoms of Nd, or we can say the phosphorus can be find out. So that can be find out by using this equation, that is, this will be given by 1 divided by 10 to the power of 8 into 4.41 into 10 to the power 22. This is the atoms of phosphorus per unit volume. So that is nothing but the density of donor atoms. So we just find out this will become, this is 4.41 into 10 to the power of, that is 22 minus 8, that is 14 per centimeter cube. So this is the following steps. By following this one donor atoms in 10 to the power 8 intrinsic atoms, germanium or silicon. Yes, Nikhil Chaturvedi, well answered. And now we are having each and every values of this particular equation. Which equation? This one. Here we can write the final equation, that is 0.026 0.026 electron volt or 26 milli electron volt, and then we are having ln. So what will the value of NC? NC is equal to 8.82 into 10 to the power of 15. Okay, no, not 15, this is 18. Okay, 18, and divided by, we just have this value, this is 4.41 into 10 to the power of 14. So we just wrote each and every values that we have found out, and the value is 0.257 electron volt. So EC minus EFN is equal to, this is equal to 0.257. Are you getting the same? Yes, some of the student has answered 0.257 electron volt below EC. So this will be the correct answer for this question. So below EC. So we are having, this will be equal to 0.257 electron volt. So since the numerator is larger than the denominator, then definitely we must have a positive value. So I just write here a positive sign here, 0.257 electron volt below EC, and this will be the final answer, 0.257 electron volt below EC, because we are going to find out the relative position of Fermi energy level in an n-type semiconductor. So statement for linked answer, and here the question number 1 we have solved. Then definitely we are having some more question that is based on similar concept, and we just want to see what are other questions. So at what doping level EF coincide with the edge of conduction band? Do you have the answer? We just have discussed these things in our previous class, in our previous slides. Okay. So at what doping level EF coincide with the edge of the conduction band? So if this is an n-type semiconductor, so I will write EFN is equal to EC minus, we are having KTLN and NC divided by ND. So in this question they will ask, given, what is given? Given condition. The condition given is, we are having EFN is equal to EC. So that means we can say this implies what? This implies KTLN NC divided by ND is equal to 0, or we can have Ln NC divided by ND is equal to 0. When we have NC equal to NC, Ln NC divided by ND will become equal to 0. Whenever we are having what? If we are having NC is equal to ND, then only it is possible. So already we have found out the value of NC. What is the value of NC? So in the previous slide we have seen the value of NC, 8.81 into 10, 8.85 into 10 to the power of 18. So since NC is equal to 8.85 into 10 to the power of 18 per centimeter cube, then we can conclude that hence ND is also equal to 8.85 into 10 to the power of 18 per centimeter cube. So that means 8.85 into 10 to the power 18 per centimeter cube. This is the answer is C. Okay. So I will have this particular answer. Very easy to answer this one. Directly we can say, but if we have the concept, then definitely we can be able to answer more number of questions that is based on similar concept. So directly we can say, whenever the ND value will have the same value of the effective density of states at the edge of the conduction band, then definitely we can say in this way. And next we are having another questions, because this is a linked question, we can answer 3 questions that is based on similar data, and then we are having the question, if the impurity concentration is increased to 4.41 into 10 to the power 19 per centimeter cube, then the location of Fermi energy level is. Okay. So, what will be the location? If the impurity concentration is increased to 4.41 into 10 to the power 19, then what will be the location of Fermi energy level? So, now tell me the answer, what will be the location of Fermi energy level? Sri Krishna has trying to attend just now, because I think he haven't seen the time, okay, because now it's 11 AM, okay. So, if impurity concentration is increased to 4.41, that means we are having now ND is equal to 4.41 into 10 to the power of 19 per centimeter cube. Previously, what will be the concentration? The concentration will be 4.41 into 10 to the power of 14 per centimeter cube. That means the concentration has been increased. Then what will be the location of Fermi energy level? So, Fermi energy level minus of EC, okay, or we can write EC minus EFN, any way we can write. So, I just write in this way also, that is nothing but EC minus EFN. This will become KT ln and NC divided by ND. Okay. Now, we know the value of NC, previously we have seen EC minus EFN is equal to KT ln. NC is equal to how much? This is 8.85 into 10 to the power of 18, and ND is equal to 4.41 into 10 to the power of 19. So, now we can see the denominator of this formula has been increased from the numerator. If the denominator is increased from the numerator, that means this is said to be a heavily doped N-type semiconductor. So, I just write here this, because of this one, I just write here this is also written by ND plus. So, that means we can say this is a degenerate semiconductor. So, if Nd plus, that means the donor atom concentration will be very large, then the semiconductor will become a degenerate semiconductor, and the answer that we are going to get here is negative. So, whatever will be the value, that value should be with a negative sign. What this negative sign representing here? The negative sign representing that Fermi energy level is moved above the lowest energy level of conduction band. So, I just write here because this is a degenerating semiconductor, then definitely we can say the Fermi energy level penetrates inside the conduction band, Previously, the Fermi energy level always located below the edge of the conduction band. Now, Fermi energy level penetrates inside the semiconductor conduction band because the donor atom concentration is increased very high. Now, we can say we are going to get a negative value, and I must say that 0.0417 electron volt above EC, this will be the correct answer, because whatever value we are getting, this must be above EC. So, this is 0.0417. So, I must write here whatever value this we can be write EFN minus EC should be with positive sign. So, if I am playing with positive and negative sign, you just cope up with me for answering this question. I just replace the location of EFN minus EC, then I can write the given thing in the positive value. So, this is 0.0417 electron volt. If I write in this way, then I must put a positive sign here. So, now the EFN will be at higher level and EC will be at lower level, and the position of Fermi energy level is lying above EC. So, we must answer, this is the answer of this question. So, if you write minus 0.0417 electron volt below above EC, then it is wrong, because if you are writing in negative sign, then definitely we have to write below EC, then it will be the correct answer. So, there are many ways to answer the question. So, in this common statement question, we have seen three types of thing. One is, initially we have seen that the location of Fermi energy level will be below the lowest energy level of conduction band, then it will get coincide with the edge of the conduction band, then it will get penetrated inside the conduction band. So, a single question will give three different values. Okay. So, three different location of Fermi energy level, 1, 2, 3. So, this is the first question. In this, the Fermi energy level locates 0.257 electron volt below EC, and here the Fermi energy level coincide with the edge of the conduction band, because the concentration of donor atoms will be exactly equal to the density of states at the edge of the conduction band NC. And here the final one, that is the impurity atom concentration has been increased, and the semiconductor will become a degenerate semiconductor, and definitely the Fermi energy level now located exactly above the lowest energy level of conduction band EC. So, this is having three different parameters. The same question is having three. Now, we are going to take the next one. In an n-type semiconductor, Fermi level lies 0.3 electron volt below conduction band at 300 Kelvin. If the temperature is increased to 330 degree Kelvin, then the new position of Fermi level assume NC to be constant with temperature is. So, very good question, because in the previous question we have seen, if the concentration of dopant atoms has been increased, how we can observe the change in the location of Fermi energy level. Now, this question is not based on the donor or acceptor atom concentration or dopant atoms concentration. This question is based on the temperature, and I already have written some concept about this particular theory that we are having here, and we can see that I have written in this. So, position of Fermi energy level depends on temperature and dopant atoms. So, we have solved three questions that is based on the dopant atoms. Now, we are having the question that is based on temperature. So, if you increase the temperature, we know the Fermi energy level will be moving closer and closer to the center of forbidden energy gap. Now, what will be the question? The question is, in an n-type semiconductor, again an n-type semiconductor, Fermi level lies 0.3 electron volt below the conduction band at 300 Kelvin. So, the temperature is 300 Kelvin, and the location of Fermi energy level is given. So, I just take this question. So, the question is question number 4, and in this question number 4, the given data we just take given. So, whatever will be the given thing, I just draw in a graphical model. So, we must draw two lines, and this is the location of the upper edge of the valence band. We just write this is EV, and this is the location of lower edge of the conduction band, and this following difference is nothing but the energy gap, and this is conduction band, this is valence band. Okay, we just know that this is x in centimeter, and this is energy in terms of electron volt. Now, the location of Fermi energy level is given. Where is the location of Fermi energy level? Somewhere here. So, what is the position and temperature? In an n-type semiconductor, Fermi level lies 0.3 electron volt. So, the difference between this is the Fermi energy level, suppose, and we just write here this is the Fermi energy level, and the difference between these two is 0.3 electron volt. Okay. So, this difference is 0.3 electron volt. And what will be the temperature? Sir, here the temperature is 300 Kelvin. So, if the temperature is 300 Kelvin, this must be the difference between EC and EFN in an n-type semiconductor. So, now the temperature has been increased. So how much the temperature is increased? 30 degree. Additionally, we have added 30 degree Kelvin in this temperature. So suppose this is temperature T1, then we are talking about temperature T2. It is equal to 330 Kelvin. Then without doing any calculation, can you tell me this particular difference will get increased or decreased? That is, we can write at T2 is equal to 330 Kelvin. So the difference between EC minus EFN will increase, okay, or decrease. Tell me this one first thing. It will increase or decrease? Yes, Hemant Nalla has said it will get increased. So I must say that yes, it increase, because as we increase the temperature, the Fermi energy level will move down or closer and closer to the center of forbidden energy gap. So we must take this particular location of Fermi energy level, and it must go down like this. It must go down like this. It must go down like this as we increase the temperature. So based on this particular thing, we can write that the difference must be increased. So do you have the options? Yes, we have the option. So we are having 0.86 electron volt below EC. So below EC, that means it is right. If it is rating above EC, then it will become a wrong answer. So this is wrong above, and this is wrong above. This is below, this is below. So there are two answers which is consisting of below EC. And these two values are greater than 0.3 electron volt. So we must have to do some calculation. Based on that calculation, we can answer this question. So that calculation is based on temperature. So what will be the formula of location of Fermi energy level in the N-type semiconductor? Sir, formula is we just take, this is EFN, the location of Fermi energy level, this is EC minus KT Ln and Nc divided by Nd, okay. So, and this is for first one, and we must write here this is EC minus EFN is equal to KT Ln Nc divided by Nd, and here we are writing the temperature is T1, and for temperature T2 we can write this is EC minus EFN. So since the Fermi energy level is changing its position, then definitely we are writing here EFN1 and this is EFN2. And we are having the formula can be written as KT2 ln Nc divided by Nd. We are not changing the donor atom concentration. So in the first one and in the second one, both the donor atom concentration will be equal. Since we know Nc is also depending on temperature. So do you have any statement which shows that Nc is constant and it is not changing with respect to temperature? If it is changing with respect to temperature, then definitely we have to find out the value of Nc also. But here written that the new position of Fermi level assume Nc to be constant with temperature. So we must mark this line that it is given that Nc to be constant with temperature. Since we know the formula of Nc, what will be the formula of Nc? So Nc is equal to, this is 4.82 into 10 to the power of 15, and we are having Mn into T divided by M raised to 3 by 2. Since Nc also consists of temperature, then we must want to find out whether something is given about Nc or not. If not, then we have to include this particular temperature, and we have to write this formula by extending this Nc to this particular formula. So it is given that Nc is not varying with respect to temperature, then definitely we can take the ratio of these two and can find out the position. So in that condition, we can take the ratio. How to take the ratio? So finally we can find out the location of Fermi energy level in an N-type semiconductor, this is 2, divided by the location of Fermi energy level in an N-type semiconductor, position 1, and this is KT2 divided by, we just write here KT1. So this will be written in this way, EC minus EFN2 divided by, what is the difference between these two? It is also given this is 0.3 electron volt, and this kk will get cancelled, and we are having this is 330 and this is given by 300. So, temperature is given and Kelvin is given. So, based on this calculation we can write this is EC minus EFN2 is equal to 330 divided by, we just write here 300 into 0.3. So, we are going to get the position 0.33 electron volt is the position. Okay. So, we have solved this question and the answer is 0.33 electron volt below EC. This is the correct answer for this question. So, I think you got these points, whatever I have discussed. Sridevi and Sarika, Hemant, Vaibhav Kumar, Narendra Reddy. Okay. Do you got this formula and the answer that we have here? So, now we have another question, and this question is a different concept. Given donor concentration as 2.63 into 10 to the power 19 per centimeter cube in silicon sample, the temperature at which the Fermi level coincide with the edge of the conduction band, if assuming Mn is equal to M. So, here we are having the donor concentration, again this is an N type semiconductor. So, and the concentration is given. So, here we are having the donor atom concentration, this is 2.63 into 10 to the power of 19, and the basic semiconductor is silicon. So, we are having silicon semiconductor, that is nothing but the intrinsic semiconductor in which we have doped the semiconductor with extrinsic material. The temperature at which, okay, we have to find out the temperature at which the Fermi level coincide with the edge of the conduction band. So, we know that if you are writing the Fermi level is coinciding with the edge of the conduction band, then the formula that is needed here is nothing but this implies kT ln Nc divided by Nd should be equal to 0, then only it is possible. Fn is equal to Ec is only possible if kT ln Nc divided by Nd should be equal to 0, which implies that Nc should be equal to Nd. So, what is the question? In this question we have to find out the temperature. What will be the temperature at which we are having Nc is equal to Nd. So, we just take another slide and we must write, if you are writing Nc is equal to Nd, we just want to know this is 4.82 into 10 to the power of 15 into Mn divided by T raised to 3 by 2, and this will be given by the donor atom concentration. And here it is also given in the question that Mn is equal to M. So, only the thing that is unknown T is question mark. So, we can write this is 4.82 into 10 to the power of 15, and we must write this is T raised to 3 by 2, and this will become equal to 2.63 into 10 to the power of how much? 19. 2.63 into 10 to the power of 19. So, temperature can be find out by using this one. So, we can find out the temperature. So, the temperature is 310 Kelvin. So, here we are having 310 Kelvin. So, basically this is another way of answering the or questioning the concepts that we have already with us, because of we have revised the formulas properly, and based on that one we come to this conclusion, that is 310 Kelvin. So, take the next one. What will be the next one? This is the 5th number of question. Then we are going to see the 6th number of question. In a p-type semiconductor, Fermi level lies 0.04 electron volt above valence band. If the concentration of acceptor atom is doubled, the new position of Fermi level is. So, we have to increase the concentration of acceptor atoms and we have to find out the new position of Fermi level. So, I am taking this question in another slide. This is next slide and I am taking the first of all given data. In a p-type semiconductor, Fermi level lies 0.04 electron volt above valence band. This is the right way of writing because already we know in a normal doping concentration of acceptor atoms in a p-type semiconductor, Fermi level always lying above the uppermost energy level of valence band. So, same thing is written here. So, now the question is for p-type semiconductor, we have done already some question about n-type semiconductor. So, this is the question for a p-type semiconductor. So, I just write here this is a p-type semiconductor and I want to draw the conceptual points that is given in this question. So, if I draw the conceptual points that is given, this is x in centimeter and this is energy in terms of electron volt and we just draw two lines to represent the two things, that is the uppermost energy level of valence band and the lowermost energy level of conduction band. So, this is EC and this is EV and the difference between these two will become the energy gap. And what will be the location of Fermi energy level according to the question? The location of Fermi energy level is somewhere here and I just write this is EFP and the difference between these two is given. What will be the difference between this position and this position? So, the difference between these two is given, this is 0.04 electron volt. So, I just write here this will become 0.04 electron volt, the difference between these two, EFP and EV. So, if you find EFP minus EV, the value will become a positive value. If you find EV minus EFP, the relative position, then the value will become a negative value. Okay. So, above the valence band, if the concentration of acceptor atom is doubled, the new position of Fermi energy level. So, we have to increase the concentration of acceptor atom. So, Na1 and we are writing Na2. So, that means if you are increasing the concentration of acceptor atoms, then definitely without knowing anything I can say the difference between these two will get decreased. The difference between these two will get decreased. Why? Because we know as we increase the temperature, the Fermi energy level will move closer and closer to the center of forbidden energy gap. If Fermi energy level is moving closer, the difference will increase and if we increase the acceptor or donor atom concentration in case of p-type and n-type semiconductor respectively, then based on these concepts we can say that as we are increasing the acceptor atom concentration in p-type semiconductor, this difference will get decreased. This difference will get decreased. So, that means based on the given data, we can say that wherever we are having the decrement in value, that will be the correct answer. So, I can say that it must be 0.022 electron volt above the valence band because all other values are greater. All other values are greater. So, based on the theory or concepts that we have, we can answer without solving the questions if the options is having only one option that is less than this particular value. That is, here we can see this is 0.04 electron volt and here we are having 0.022 electron volt and all others are greater than this one. So, Sri Devi has answered yes. We are having the answer that is given by this 0.022 electron volt above valence band. But we can solve it by using the formula. So, this is given by twice of Na1 we can write and this is Na1, there are two different concentration. So, I can write the formula for an p-type semiconductor, that is EFP, okay, Fermi energy level, this is given by EV plus this is KT Ln and we can write this is NV divided by Na, not Nc, this is NV divided by Na. And we can write by using this one what will is Na, the acceptor atom concentration. Na is equal to, we can take this is EFP minus EV, EFP minus EV, that means this particular value, and we are having this is KT. KT can be taken denominator of this one and e raised to, and we can write this is in this way. Okay. So, we can write this is e raised to, this is EFP minus EV upon KT upon KT. Okay. And we are writing here, this is given by NA is here, we can write here NV. So, this is another formula by which we can find out the acceptor atom concentration in a p-type semiconductor. So, what will be the formula? Formula will be acceptor atom concentration is equal to NV e raised to EFP minus EV upon KT, if it is correct, because Na is the denominator. So, we just mark a negative sign here. So, this is the formula by which we can find out the relative position of the Fermi energy level in an p-type semiconductor, and I can see this is the formula by which we can proceed. This is the formula by which we can proceed. So, negative sign will be there. So, based on these concepts, we can write, we are having two acceptor atom concentration Na2 divided by Na1 we can write, and this is given by NV, and here it is also NV, and e raised to minus of this is EFP2 minus EV divided by KT. So, we just write here divided by KT, and here this is also e raised to minus of EFP1 minus EV divided by KT. So, this is the formula by which we can find. Okay. So, I can write here, this is twice of Na1, this is Na2, and this is Na1, and NV and V will get cancelled, and we are having this is EFP2 minus EV. That is what we have to find out in this particular question, and we know this is e raised to minus EFP1 minus EV, already we know this is equal to 0.04 electron volt divided by KT. Okay. So, we know the value of KT, since we can write, since KT is equal to 0.026 electron volt. So, I just take this value, and we can write this is 2 is equal to, because this Na1 will get cancelled, and we have to find out the relative position of Fermi energy level in case of second minus EV divided by, we just write here, this is 0.026 divided by, we are having this is minus of 0.04 divided by 0.026. So, only unknown thing here is nothing but EFP2 minus EV. So, we can write here, so what will be the answer after solving this one, EFP2 minus EV, this will be given by 0.022 electron volt. .022 electron volt above the valence band. So, this is the way by which we can solve the question. Okay, Sri Devi got the answer. Answer is 0.022 above valence band. So, here we cannot say this semiconductor is degenerate semiconductor. The reason is that the location of Fermi energy level here also is above the location of uppermost edge of the valence band, that is EV. Because the answer is positive, that is why we can say that The location of Fermi energy level is again above the valence band, edge of the valence band. So, the new position of Fermi energy level can be drawn in this particular graphical plot only, and if you draw the new position of Fermi energy level, that is located somewhere here, but the difference between these two will get decreased. The reason of decreasing in distance is nothing but the addition of added dopant atoms, that is nothing but the acceptor atoms in the similar semiconductor. And of course, I will write that this is EFP2, then this particular position is nothing but, this position is nothing but okay, EFP1. This is EFP1, and here this will be the new location of Fermi energy level, and this is EFP2. The difference between these two, okay, understand the concept. The difference between these two is simply we can write this is 0.022 electron volt. So, previously it was 0.04 electron volt, now it will become 0.022 electron volt. So, very interesting, very conceptual. We have to change the formula somewhat to get the answer quickly, otherwise we have to do so much calculations. So, in this way we can do the or solve the question that is based on the increasing the dopant atoms in a p-type semiconductor, and we have to find out the exact location of Fermi energy level based on that concept. So, I will take the next question, whether we are having any more question. The Fermi level in an n-type semiconductor germanium bar is 0.2 electron volt above the intrinsic Fermi level towards the conduction band. The conductivity of the bar is in ohm centimeter inverse, okay. Given Ni is equal to 1 into 10 to the power 13 per centimeter cube, mu n is equal to 3500 centimeter square volt per second, and mu p is equal to 1500 centimeter square per volt second. So, this is another question, and this is yet a conceptual question. So, I am waiting for 30 seconds to get the answer by you, then I will solve this question. So, how many of you attending the classes? From which state you belong? Tell me once. Okay. So, Sridevi, Joseph Bright, okay. Those who are attending the classes, they once tell me from which state they belong to, and after that one you just try to solve this question. Joseph Bright is from Mumbai, Sridevi is from Andhra Pradesh, and Hemant Nalla is from Telangana. Rest of the students from where they are belonging to. Narendra Reddy is from Telangana. Good. And what else? Lakshmi, I am from Tamil Nadu, sir. Welcome, Lakshmi. And Mansoor is from Andhra Pradesh. Maz Mansoor. Prithvi Srinivas is from Karnataka. Okay. And Janardhan Rao is from Andhra Pradesh. Very good. Very happy to see you all at this stage. And I must excel your knowledge by using different conceptual questions and conceptual points if you are not attending any classes. Okay. Thank you everyone. You just join Gate Academy Global channel for getting the proper idea that what is the time of the live classes, and some motivation thoughts also I am sharing there. You just join, and you can join my channel also, my group, okay, my personal group of Shishir Das, and there also we are going to solve many of the conceptual questions, and we are having some motivational thoughts and every morning. So, if you like that one, you just give me an acknowledge that sir, I am very much motivated by your written statement that you have given. So, do you have the answer of this question? The Fermi level of an n-type germanium bar is 0.2 electron volt above the intrinsic Fermi level. So, for understanding this one, we just want to draw the diagram that is similar to this one. Okay. So we are going to solve the question number 7. Okay, question number 7, and in this question number 7, what is the thing that is given? The Fermi level of an n-type germanium bar. So we are having a germanium bar, and we are having a germanium bar, and this is doped with some pentavalent atoms, then it will become an n-type germanium bar. Okay. Then what else? A bar is 0.2 electron volt above the intrinsic Fermi level. So now again the relative position is given, but the relative position is not given with respect to lowest edge of the conduction band. It is given with respect to intrinsic Fermi energy level. Since this question is different, I want to draw again the graphical plot to give you a proper knowledge of this particular question. So we are having this position is nothing but the position of EC and another position which is representing the position of EB, the uppermost energy level of valence band and the lowermost energy level of conduction band. This is valence band and this is conduction band. Where the holes locates, the holes locates in this particular energy band diagram? Tell me once by your comment in the comment section. Okay. Now we are having in an n-type semiconductor germanium bar 0.2 electron volt above the intrinsic Fermi energy. Since we know that the position of intrinsic Fermi energy level is always taken at the center, and this is by default we are taking this is the position of intrinsic Fermi energy level, and this is always located at the center, that is EC plus EB divided by 2, and this will be the center. And in this question we are having the position of Fermi energy level which is locating somewhere here, I think. Okay, this is the position. Okay, what will be their position? The position is 0.2 electron volt above the intrinsic Fermi energy level. So I just write here this difference, the positional difference between these two, this one and this one. This will be given by 0.2 electron volt, 0.2 electron volt above the intrinsic Fermi energy level. So I just write here this is the position of Fermi energy level in an n-type semiconductor. So now towards the conduction band, the conductivity of the bar is, so we have to find out the conductivity. Conductivity means sigma, and in an semiconductor conductivity can be found out n q mu n plus, this is like a song, p q mu p. Okay, so this is the formula, and we just have to take care, mu n and mu p is given, and n and p we have to find out, and what else? Nothing else is given. Since it is an n-type semiconductor, I just write the formula properly by writing with subscript here, which is representing that we have to find out the conductivity of an n-type semiconductor. So sigma n is equal to n in n-type q into mu n plus p in n-type q into mu p. Thank you, Sridevi, your motivational is really helpful, sir. Thank you. And we have to find out the this n in n-type and p in n-type, because q is 1.6 into 10 to the power minus 19, and mu n and mu p is given. So we know this one, we know this one, we know this one, we know this one, but we don't know what is n in n-type, this is a question mark, and what is p in n-type, this is a question mark. To find out these two values, we only have one data, that is the relative position of intrinsic Fermi energy level and n-type Fermi energy. We have the formula, that formula is nothing but the comparison of this relative position, that is EFN minus EFI, and that is given by, this is KTLN. Okay, this is given by KTLN, and this is ND divided by NI. This is another formula, and this formula is a star mark formula. This formula is a star mark formula. because we are going to use this formula many times, and I must challenge you that up to MOSFET you have to remember this formula, that is the relative position of EFN minus EFI, the intrinsic Fermi energy level, that is given by KT ln ND divided by Ni. Okay, so this is the formula. From this formula we can find out the value of ND. So if you can be able to find out the value of ND, then it will be okay. So we can write ND is equal to, this is given by Ni into e raised to, this is EFN minus EFI divided by KT. So by this equation we can find out the value of ND. What is ND? Sir, ND is nothing but the value of N in N-type semiconductor. This is given by ND. So that's why we are going to find out the value of ND. So ND is nothing but this is N in N-type semiconductor, and it will be given by Ni into e raised to the EFN minus EFI. So it is I, EFI divided by KT. Okay. So by using this formula we can find out the value of ND. So we just write again to find out the value of ND, the final one. So ND is equal to N in N-type semiconductor is equal to Ni into e raised to, this is EFN minus EFI divided by, we just write this is divided by KT. So how to find out the value of Ni? So Ni can be found out by using, Ni is already given. So we have to find out the value of ND. What is Ni? Ni is how much? 1 into 10 to the power 13. This is given by 1 into 10 to the power of 13 into e raised to. The relative position of these two is given, that is 0.2 electron volt, and the temperature is not given, so 0.026. So by using this one we can find out the value of ND. So tell me what will be the value of ND first, and if you know the value of ND, then we can find out the value of P in N, that is given by Ni square, mass action law we have to apply, Ni square divided by Nd. What is Ni square? Ni is nothing but the intrinsic concentration which is given in the question, that is 1 into 10 to the power 13 square. So this is 1 into 10 to the power 13 raised to 2 divided by the value of Nd that we found just now. So by using these two values we can put the values here and here, and we can get the answer. Very simple one, very easy one, but we just need to have these two formulas. So I think the answer is this one. Sri Devi has answered this one. 12.2 sir, option A. Are you getting the same? Tell me once. So can you have the derivation part? So this is your assignment. Do you have the derivation to find the formula of the relative position, that is EFN minus EFI is equal to KT ln ND divided by Ni, and this is the first one, this is the second one, that is EFI minus EFP is equal to KT ln, this is Na divided by Ni. So tell me, do you know this derivation part of this one? So your answer should be yes, yes, we know, or no, we don't know. These are the two different formulas, and that is very important. Okay, many times we are writing very. So this is a negative statement, very important. Okay. So we are having this two one. So this is the final one, and we are having 12.26. Okay, and ohm centimeter inverse, the correct answer of this question. Yes sir, yes sir, yes sir. So this is the final question, I think, and you just take these two formulas into your account, because these two formulas are very important for understanding, and the unit of this particular in is ohm centimeter inverse. Okay. So Joseph from Mumbai and Sridevi from Telangana, Andhra Pradesh, yes, they answered that, they know this one. Okay, so this is the final one. We don't have any more questions right now, and we are just going to stop the session here. Okay, and another question. Effective mass of electron is equal to thrice the effective mass of hole. The distance of Fermi level in an intrinsic semiconductor from the center of forbidden gap is dash below the center of EG. So for this one, how we can proceed? The procedure to solve this question is nothing but the formula of the Fermi energy level in an intrinsic semiconductor, and this is given by EC plus EV divided by 2, and this is minus of KT divided by 2 ln, and we are having NC divided by NV. By using this formula, we can solve this question. Effective mass of electron is equal to thrice the effective mass of hole. So that means the mass of electron will be greater than the mass of hole. So for solving this question, we just take another slide, and by using that slide, we can solve this question. So we are having the 8th question, and the position of Fermi energy level. This is another way of asking the similar question. Divided by 2 minus KT divided by 2, and we are having ln NC divided by NB, very easy one. Okay. And we know the formula of NC. What will be the formula? This is 4.82 into 10 to the power of 15, and we are having this is MP. Okay, we are having Mn into T divided by M raised to 3 by 2. And similarly, we are having Nv, this is equal to 4.82 into 10 to the power of 15. And of course, we are having Mp into T divided by M raised to 3 by 2. If you take the ratio of these two, then the only left out parameters at similar temperature is nothing but, so this will be given by the Nc divided by Nv. What will be the ratio, sir? Mn divided by Mp raised to 3 by 2. So if we have the relationship between the effective mass of electrons and effective mass of hole, then you can be able to solve the question. Effective mass of electron is equal to thrice the effective mass of hole. So we just write here, this will be given by 3 raised to 3 by 2, because from the given condition it is given that, we just write here, since given condition is that effective mass of electron is equal to 3 times the effective mass of hole. So based on this concept, we can write the distance of Fermi energy level in an intrinsic semiconductor from the center of forbidden gap is, that means they are asking the relative position. If they are asking the relative position, we just take this equation. Which equation? This one. We just write this equation. This is given by EC plus EV divided by 2, which is nothing but the center, minus EFI is equal to, this is KT divided by 2 ln, and we are having 3 raised to 3 by 2. And since temperature is not given, we are taking room temperature, and we can write this is 0.026 divided by 2 and ln 3 raised to 3 by 2. Mayank Tiwari, thank you very much, sir. I am at lecture number 19, but continuously following crash course. Thank you, Mayank. You just going to get a very good concept of EDC if you are following all the lectures. Okay, follow all the lectures, and very soon you are going to be connected with the similar lecture that I am going to take live. Okay. So, this is the formula. By using this one we can get the answer. So, tell me once what will be the answer. What will be the answer? Tell me once. We can take 3 by 2 outside and then solve by finding out the value of ln of 3. Booklet. Nobody solved this one. Do you have calculators with you? 0.00335. Anyone else? So, we got 3 answers from 3 different person. Sri Devi 0.0335 and Sri Krishna 0.014 and Lakshmi 0.2 sir and Narendra Reddy 0.021 and Hemant Nanla 0.0321. I did mistake 0.0214. So, this will be the correct answer, I think. So, the answer is 0.0214 electron volt. You are getting various answers. I don't know why. So, did you solve this one? So, it is like somewhat like this 0.02 electron volt. We just normalize everything and we have answered this one. So, we just solve each and every points that we are asking about intrinsic semiconductor. We have solved questions about extrinsic semiconductor, either it is N type, P type, and we have changed the formulas many times for answering this question. And what will be the formulas that we have seen today? What are the formulas? You should write all those formulas in your short notebook, okay, so that you can revise the formulas. And in addition to that, the questions that you are facing difficulties, you just take that questions in your notebook, that is short notebook, that in which you are facing difficulties. So, short notes consist of the formulas, some steps that is required to get the concepts behind those formulas, and it should be added with the questions, only those questions that you are facing difficulties while solving mock test or while solving the question pattern that you are following from any workbook. Okay. So, if you are writing the short notes properly, then definitely whenever we are facing examination like mock test. So, if you are having mock test today at afternoon, you are trying to solve, then before that one, before 2 hours, you just revise those short notebook in which we are having formulas, some concepts about those formulas and some question based on those formulas that we are facing difficulties. Then your mock test or overall test that we are going to face after 2 hours will be gone very good, and you will get very good marks in that questions, and definitely this will motivate you, this will increase your confidence. Then you should follow the following step that I just told you. Okay, so now I am signing up, and I will meet you tomorrow at 11 p.m. and just connect with me by using these Telegram channels. Okay, I will give you some motivation based on, I will give you some thoughts that I have based on my experience. Okay. So, till then, thank you everyone and bye.